Okay, we're going to move into the third chunk of the day now, and we're going to move up to the northeast. And I didn't know there was this much life in the northeast, but there apparently is. I'm not a politician, no. So I'm now going to welcome Professor Julia Newton to the platform. Sonia mentioned it, but earlier this week Sonia took the small group of supporters she was talking to visit Newcastle and Northumbria universities to find out more about the work that these donors were actually helping to fund. Julia described MEs and CFS research as being core business for these universities, which just that statement alone is an exciting thing to hear. And I think during the visit, the high visit of collaboration, enthusiasm and determination that was shown by Julia and indeed Jason's team that we'll come to shortly was exceptional and was little short of getting these guys to get their checkbooks out while they were standing there. So it just goes to show that this level of commitment, passion and enthusiasm really can drive, it's self-fulfilling, it will drive yet more action, which I think is fantastic. Julia is the Dean for Clinical Medicine at Newcastle University and has a clinical and research interest in the symptoms of fatigue. She has a background in investigating and managing fatigue in chronic diseases, including liver disease, renal disease and chronic fatigue syndrome, and is currently researching the role of autonomic dysfunction in the pathogenesis of and severity of fatigue and ME and CFS, and actually has spoken to us before, and I enjoyed it so much. Guess what? You're back. So, Julia, over to you. Thank you.
Great. Thank you very much. It's a great pleasure to be back here again with Action for ME. I'm having quite a week of Action for ME, which is fantastic. I have to start off by apologising to say that straight after this I've got to go and get a train because I've got a family commitment back home in Newcastle, so I'm on the 3 o'clock, so I'll miss Jason's talk and Alina's, unfortunately. So what I'm actually going to focus on for the next 10 minutes or so is very specifically the project that Action for ME and yourselves have very kindly funded. She'll hate me for this, but Gina is one of the futures of ME CFS research in Newcastle. She's a PhD student, and I googled her to find a picture, and this was the only one I could find. So if she happens to watch this on the YouTube channel, she'll not be very pleased with me. But Gina is now supported 50% by an Action for ME grant. She's got a 3-year PhD studentship with myself and a chemist called Phil Manning, and she's working on a project to look at muscle function and developing a drug pre-testing system using muscle cells, which I'll come on to talk through with you in the next few slides. So she's a real live example of the work that you do and what benefits it can lead to. So in terms of muscle function, the work we've done in the past using muscle MRI has allowed us to examine how acid accumulates in the muscles of patients with ME/CFS. And we've done a series of experiments now where we've asked patients to exercise in the magnet of the MR scanner. We've done baseline exercise and then repeat exercise. And we've published that in 2 papers now in work that was funded originally by ME Research UK. And what we were able to show during those experiments was that patients with ME/CFS accumulated huge amounts of acid within their muscles, and the exposure that the muscles have from acid during exercise and between bouts of exercise was extremely high. And that also patients with ME/CFS had problems related to muscle bioenergetic function with an anaerobic threshold that was significantly lower in patients with CFS-ME compared to normal controls. When we were doing these muscle MRI experiments, one of the things that we also noticed was that there were 2 distinct groups of patients when they were exercising in the MRI scanner. There was a group that we named Group 1, where they depleted their phosphocreatine as we would expect during exercise, and a second group that didn't deplete their phosphocreatine and didn't accumulate acid within their muscles. So there were two different phenotypes, which goes back to the talk from Stephen this morning, that there are very distinct groups of patients within this umbrella diagnosis of ME/CFS. So from our muscle MRI studies alone, we were able to show that there are two different types of muscle abnormality in patients with ME. The patients who participated in the muscle MRI studies then very kindly, 10 of them, gave us a donation of muscle cells. So they had a muscle biopsy, and these are muscle cells just here, and then we can actually grow these muscle cells into muscle tubules, which are long tubes of muscle cells. And the aim of those experiments was to actually, in the laboratory, so in vitro, develop an exercise system whereby we could replicate the work that we'd seen in the MRI studies, but also in the laboratory use those muscle cells to exercise them and see what happens within those cells in response to exercise. And the particular things that we were looking at in this muscle cell laboratory system was something called AMP kinase and how that was activated. That's an enzyme within muscle cells. A molecule called lactate dehydrogenase, which is something that we use to show that exercise has been happening efficiently within muscle cells. And we also looked at uptake of glucose into muscle cells and how things like IL-6, which is a cytokine, an inflammatory marker, how the IL-6 was expressed and subsequently secreted within muscle cells. And this is the system that we used. This system is our exercise laboratory. And you can see here that there's some 6 wells here where we put muscle cells from our patients with ME/CFS. And then over the top we put this special plate, and then through this ribbon cord, electric impulses are given to the muscle cells to known amounts of exercise. So why did we choose the things to measure that we measured? Well, AMP kinase is something that we know is a cellular protein that is involved in energy metabolism within cells. And we know that it's activated by a low energy status, such as during exercise. And there are a variety of different mechanisms by which AMP kinase can be switched on or switched off during exercise. We also were very interested in looking at how glucose is taken up into skeletal muscle cells, because we know that sugar is a substrate for AMP kinase, and we know that it's involved in muscle bioenergetic function, and it's very easy for us to measure how much glucose is taken up into skeletal cells in the laboratory. And this is just a schematic to explain how these interact. So insulin is involved in taking up of glucose into the cells and during exercise. And there's a variety of different ways that exercise can modify the uptake of glucose, and ultimately is involved just behind Jason's head there in the activation of this molecule AMP kinase. And then the other thing we wanted to measure was IL-6. Now, interleukin-6 is a molecule that's involved in inflammation, and it's been long recognised that muscle is an organ that is able to produce and secrete cytokines. From muscle, they're called myokines. So it's able to release myokines such as IL-6, and this is involved directly and indirectly in contractile activity within muscle cells. So by measuring this, we were able to look at how the muscle was functioning and look at the intensity and duration of influence that IL-6 had upon muscle cells. And this again is just a schematic to show how IL-6 again can be involved in AMP kinase activation. It can also, once released, have actions upon other organs outside the muscle, such as the liver, and lead to release of glucose from the liver in response to exercise and from adipose tissue. So, what do we actually do? Well, once we had the muscle cells, we're able to subject them to our protocol, where after a lot of experiments we were able to define what was the most ideal exercise protocol for the muscle cells, and we chose a protocol that was bouts of electrical stimulation to replicate more appropriately the activity that might happen on a day-to-day basis by a patient with ME/CFS. So rather than constant contraction of muscle cells such as might happen in a marathon, we gave low levels of activation more representative of real life. And we were able to see muscle contraction within the muscle cells and also show that the levels of LDH, or lactate dehydrogenase, confirmed that we weren't damaging the cells using this exercise protocol. So the cells weren't being barbecued, that we were actually effectively exercising these muscle cells. So this is just a video that when Audrey managed this for the first time, who's one of the postdocs in the lab, it was very exciting. And you can probably just see from here, this little video, that we can actually visualize the muscle cells contracting during the stimulation from the exercise rig. So what do we find? Well, in terms of AMP kinase, what Gina and Audrey have been able to show is that in the normal circumstances, there's an activation of AMP kinase, which is stepwise and peaks at 16 hours of stimulation. In patients with ME/CFS, you can see that this pattern is very different, that there is not an overall activation of AMP kinase compared to the controls. So there's a difference in how AMP kinase is activated in muscle cells from CFS ME patients compared to controls. In terms of glucose uptake, this is basal levels of glucose uptake. When we add insulin into the experimental wells, when we exercise the muscle cells, and when we exercise the cells and add insulin, and there's a stepwise increase in glucose uptake into the muscle cells. In control patients and in patients with chronic fatigue syndrome, you can see that it doesn't happen. There's a very slight increase with insulin, but exercise doesn't add anything further when we add that as well as insulin. So again, obvious differences between CFS and control patients. In terms of IL-6, again, I'll not reiterate this, but there is an obvious difference between the control patients and chronic fatigue syndrome patients in terms of expression of RNA. And when we split these down into those two different muscle phenotypes, it was clear that the two different muscle phenotypes, group 1 and group 2, have different patterns of how they express IL-6. And then if we look at measuring the protein itself, again, there are significant differences between the CFS population and the controls, and between those two different groups of patients within the overall group of ME/CFS. So in terms of summarising some of the results that we have today, we now have a system that allows us to exercise muscle cells efficiently and effectively in patients with ME/CFS, that allows us in the laboratory to begin exploring these pathways of abnormalities that we've detected, to look at means by which we can begin to modify some of these abnormalities and understand what might be leading to these abnormalities in the first place. So in terms of the muscle exercise, what we've been able to show is that there is a skeletal muscle abnormality in patients with ME/CFS, which we believe to be at the level of AMP kinase or upstream of AMP kinase. If we're thinking about the acid that we've also shown to accumulate at high levels within the muscle cells of patients with ME/CFS, we could also begin to speculate that this may be happening at the level of a molecule called pyruvate. And pyruvate dehydrogenase kinase is another enzyme that we know is responsible for the pathways within muscle cells that might lead to the accumulation of acid and ultimately muscle dysfunction. And there are molecules, one of which is called DCA, or big long name dichloroacetate, that we know can modify PDK and ultimately cause a reduction of acid accumulation and movement of those pathways back towards normal muscle function. And we've developed a sensor system, which is something that Gina is working on at the moment, whereby we can actually, in that muscle exercise rig, encourage something called nanosensors to go across the muscle cell wall that fluoresce at various different pHs, so that we can measure the pH actually within the muscle cells while we're exercising them. And this is just a schematic to show how we do that with a variety of different dyes that fluoresce at different pHs. We get those nanosensors into the cells using something called a transfection system, which allows the cells to absorb the nanosensors without actually destroying the cells, and we're then able to exercise them while visualizing how much acid there is within the muscle cells. And this just shows you how we can see the little nanosensors and the fluorescing at various different pHs, and over time that disappears. So it doesn't destroy the cells, but over time they stop fluorescing as there's less acid there. So in terms of where Gina's going now, she's only a year into her 3 years of her PhD. She's looking at detecting extracellular chemicals within this muscle exercise system, looking at how we might modify extracellularly what's happening to muscle cells. She's isolating mitochondria and investigating how mitochondria and knockout agents might influence how cells metabolize. And then she's also developing this intracellular detection system using analogues of this chemical DCA, which would be safe in humans, whereas DCA would be toxic to humans, to actually begin to tease out drugs that we could fast-track to clinical trials that may be able to reverse the acidosis that we found on the muscle MRI scans. I started off by saying thank you to Action for ME, and it's important that I finish off by saying thank you to Action for ME. We're hugely grateful to Sonia and her team for the support that they've been giving us. And Gina, I'm sure, will come along perhaps next year and give you a full resume of where she's at. And she is a credit to the investment that you've made in her. Thank you.
That was great,